Hello Year 12 and welcome to the fourth video here for our second topic. We're looking at linear functions. Linear in this sense forms a straight line. Okay, if we graph these things, we get a straight line and not a vertical line for that matter. Right, a straight line. A function is like a number machine. Numbers go in, numbers come out. The numbers that go in we call independent variables, and they're most commonly represented by the pronumeral x. So that's what goes in. Out the other side comes our independent variables, okay, and they're most regularly represented by the pronumeral y. X goes in, y comes out. Linear functions can always be written in the form y equals mx plus b, where m is the gradient, how much it changes, how quickly and in which direction my values are changing all the time. And b is the y-intercept, and that's perhaps we might refer to as the initial value, right? It's the value of the dependent variable when the independent variable equals 0. Right? What that means is it's under a 0 in the table of values. And it's where the graph of this line crosses the vertical or y-axis. Now, we are going to look at a table of values and calculate the gradient and the y-intercept so that we can write the equation of this function. We find the gradient by finding a pair of coordinates, finding the difference in the dependent variable, the difference in the y, divided by the difference in the independent variable, the difference in the x. We're going to jump straight into an example here, and the two pairs that I'm going to use are going to be this pair and this pair. So to find the gradient is the difference in the y's, that's 3 minus 1, divided by the difference in the x's, that's 2 minus 1. Okay, this number minus this number, divided by this number minus this number. Now, whether I choose those ones, whether I choose my first and last pair there, I'm still going to get the same gradient here. But anyhow, when I evaluate that, I get m equals 2, and that's really important. That's part of my answer. Right, so don't lose track of that number there, m equals 2. Now in this case here, it's quite simple to find b because it is simply the number underneath the 0. So that means that in this case b equals -1. I don't have to calculate it, I can read it from my table of values. So now I rewrite this as y equals, instead of m, I say 2, and instead of b, I say -1. So y equals mx plus b. My gradient is 2, my y-intercept is -1. My equation, my function here, still has the x and y in it. Now we might sometimes substitute into that equation to help find the y-intercept. I'm going to show you how that works here in example 6. But first of all, we need to find the gradient. I'm going to do that using, I think, that pen never works, these pairs here. Right, but any two pairs of coordinates are going to be fine. So, my gradient is the difference in the dependent variables. That's the bottom row. Here is going to be, and I'm just going to put a little x and y here as a reminder. They're not actually x's and y's. In this case, we've decided to use v and c, but we treat them exactly the same. So the difference in the bottom line, if you like, of my table is 104.75 minus 98.8 divided by or over 15 minus 8. Okay. Now if I punch that into the calculator, I'm pretty sure I get m equals 0.85. Okay, remember, that's an important part of my answer. That's going to score you some marks in this question if you don't go any further. We should go further. It's not too hard to do so. I can't read the y-intercept off here, off my table of values, because I don't have I don't have a 0 in the top row. Right? I'm looking for the number underneath the 0, I don't have it there, so we're going to substitute into y equals mx plus b. But I'm also going to substitute an x and a y value. So if we consider, consider a pen that works, y equals mx plus b, that's what we're going to substitute into. I'm going to replace my y in this case with 98.8. 98.8 equals mx, that's 0.85x. Oops, not x, because I'm going to replace x in this particular example with an 8. Okay, I'm putting in a coordinate pair there. Plus that unknown b. Now when I rearrange that, I think I get 98.8 equals 6.8 plus b, subtracting 6.8 from both sides, and I get b equals 92. That means my linear formula is y equals 0.85x plus 92. But in fact, I should adjust that because we haven't used x and y, we've used v and c. So let's just swap those around, and I'll say that my cost c equals 0.85 v plus 92. And you could check that out, right? You could substitute what happens if v equals 20, 0.85 times 20 plus 92 to be 109, for example, right? I now have a formula for extending that table of values, perhaps. Now, what does the gradient represent? We've got to read these things fairly carefully. The cost of water usage. So for some volume of water, this is how much it costs. The gradient tells me how much it changes. So in fact, what this is going to be, the gradient, every time I use an extra kilolitre of water, my cost increases by $0.85. So what the gradient is representing is the cost per litre of water, which is 85 cents, if we like, per kilolitre. Oops, per kilolitre of water. Right, kilolitres here. Right, so the gradient is the rate of change. Okay, and what that's going to represent in a linear model is going to have the word per in it, something per something. What does the vertical intercept represent? Well, that tells me that if I use 0 litres of water, it still cost me $92. So it's sort of like a flat rate, like an access charge, a fixed charge, like an access charge. Let's write that. For water supply. Okay, because that $92, the vertical intercept, that doesn't change depending on how much water I use. Okay, I pay 85 cents for every kilolitre of water I use, but I've also got to pay $92 regardless of how much water I use. So that's what my y-intercept represents, is a constant charge or a constant amount. The gradient represents a rate of change. The y-intercept represents a fixed amount and an initial amount. Now, what is the independent variable? And what does it represent? Independent is the top line, so the volume of water used. And that was represented by a V in this question here. Now, there's a lot of work in these. You can expect when you do a topic test or an assessment task that relates to these, to see one of these questions. A very important part of the topic. They're always reasonably tricky. There's quite a few processes to go through. It's well worth practicing these and getting on top of them. Right? I really stress that these are common questions to see. It's a fairly regular process that you go through. It looks like we're doing lots of processes now, but you do a very similar process for each one of these questions. Check out the video, plug away at some other examples, at some questions through the textbook, and make sure you ask your teacher if you need any help. Okay, good luck.